Assalamualaikum and hello everyone. My name is Nuhusna Mushida and today I will present my final year project entitled Effect of Vanadium plus Nitrogen coupled with LiFePO on Structural, Electronic and Electrochemical Properties, the DFT study. This project conducted by Dr. Ahmad Fairoz and Dr. Fadil Wafi. So these are my overview for today's presentation. I am interested in this topic because of the growing focus on renewable energy, especially in the development of rechargeable batteries for electrical vehicles (EVs). So as you can see in the picture, Malaysia has launched its own EV, the e-Moth, showing our country is commitment to green technology. So batteries like LiFePO play an important role in powering these vehicles due to their safety, stability and environmental benefits. So this inspired me to explore how materials like LiFePO can be further improved through doping for better performance in real-world applications. Next, we move to the advantage of lithium iron phosphate of LiFePO. Discovered in 1996, LiFePO quickly gained popularity as a cathode material in lithium-ion batteries. It's widely valued for its high safety, excellent thermal stability, and environmental friendliness, which makes it ideal for use in electric vehicles, solar energy systems, and portable devices. LiFePO offers a theoretical capacity of 170 mAh and a lithium intercalation potential of 3.5 volts. These properties make it an efficient and reliable energy storage material. So overall, LiFePO provides a safe, stable, and sustainable solution for modern energy needs. While LiFePO offers many advantages, it is important to also consider its limitations. So one major drawback is poor performance at low temperatures, which can affect battery efficiency in cold climates. It also has a lower energy density compared to other cathode materials, meaning it stores less energy per unit of weight. Additionally, LiFePO suffers from low ionic conductivity, which limits the speed of lithium-ion movement within the material. So how can we address this disadvantage? So one effective method is through doping, a process where foreign atoms are introduced into the LiFePO structure. So doping can improve the electronic structure and enhance the battery's overall performance. So for doping to be successful, the dopant's ion should have a certain characteristic. So for the first one is their ionic size should be similar to the ions where they replace to avoid crystal distortions. The second one is they must maintain the charge balance within the structure. To overcome the limitations of LiFePO, researchers have explored various doping strategies. Among them, vanadium and nitrogen have shown promising results. So let's start with the vanadium dope. So vanadium was chosen because its ionic radius and charge are similar to ion Fe2+, making it a suitable substitute within the LiFePO structure. So it also integrates well into the crystal lattice without causing major distortions, and it may significantly improve electronic conductivity and enhance the structural stability. Next, we have a nitrogen doping. So nitrogen's atomic size is close to that of oxygen, which allows it to replace oxygen atoms in the structure without causing severe strain. So this substitution leads to the formations of Fe2+ or Fe3+ mixed valence states, which improve electronic conductivity by enabling better electron flow. So as a result, nitrogen doping may enhance both electron conduction and lithium-ion diffusion, leading to improved battery performance. So these are the main points from the literature review that I got from the several sources. So I also look at the other related articles to support my research. Next, we will moving on to the problem statement. So for the first one is LiFePO has low ionic conductivity that would hinder the movement of lithium ion in charge and discharge process. For the second one is the structural distortion caused by doping with new materials. So for the objective, to enhance the ionic and electronic conductivity of LiFePO cathode material by doping vanadium and nitrogen. The second one is to optimize CODO lattice structure via geometry optimization. And the third one is to obtain structural, electronic, and electrochemical properties of CODO via DFT. So this is an overview of the methodology that I used throughout the study. So these are the crystal structure that I used in this study. So for the first one is LiFePO, the original structure. The second one is LiVPO4, where vanadium replaces some of the ion. Then the LiFPN, where nitrogen replaces some oxygen. And the last one is the LiVPN, which is CODO of the vanadium and nitrogen. So all of these were optimized to make sure the structures are stable. Now we continue with the result and discussion section, which highlights the key outcomes of the structural, electronic, and lithium-ion migration analysis. Now let's look at the structural properties of LiFePO and its dope variants. So as shown in the table, unit cell H lengths along the crystal axis pure LiFePO for A 10.304 Armstrong, B 12.048 and C 4.659 in this work. So these values closely match previous studies such as Wang and Wang reported parameters. So these alignments confirms that the accuracy and reliability of our result. For the sample dope with the vanadium and nitrogen, the change in lattice parameters are very small. So this indicates that the lattice stability is well maintained despite the doping. So additionally, the unit cell volume changed minimally from 582.781 Armstrong in the pure LiFePO to 582.966 in the dope sample. Such minor volume change suggests minimal lattice distortion. So the maintaining such small distortion is important because it helps to preserve the material's crystal structure, and which is essential for the stable battery performance. Now, I will explain the electronic properties of my study, focusing on the band gap and how it affects the conductivity. So a smaller band gap means better electronic conductivity, which is important for lithium-ion battery performance, especially during fast charging and discharging. And in this study, I used the FT calculation to check the band gaps of pure and doped LiFePO. So the pure LiFePO has a band gap of 3.709 EV, which is make it an insulator with poor conductivity. So after vanadium doping, the band gap drops to 2.097 EV, showing better conductivity, and with nitrogen doping, it decreases further to 1.192 EV, improving it more. So the best result is from the co-doping with vanadium and nitrogen, which gives the band gap of 0.835 EV. So the lowest value meaning the highest conductivity. So this shows that the co-doping is more effective than using either vanadium or nitrogen alone. In addition to the band gap, I also look at the heat density of state DOS to understand how doping affects the conductivity. So for the pure LiFePO, the DOS shows a clear gap at the Fermi level, meaning there are no available electrons to conduct electricity. So it confirms that it has a poor conductivity. So with vanadium doping, the new V3D states appear near the conduction band. This helps reduce the band gap and allows the electron to move more easily, so that it shows that it improves the conductivity. So for the nitrogen doping, we see the N2P states near the valence band, so which also narrows the band gap and boosts conductivity. So the best result is in the co-dope sample. So both 3D and N2P states appear near the Fermi level, creating extra path for the electron movement. So this leads to a much smaller band gap, only 0.835 eV. So it concludes that co-doping with vanadium and nitrogen not only narrow the band gap but also increases the DOS near the Fermi level. So it resulting in the highest electron conductivity, which is great for battery performance at high charging and discharging rates. So next, I will discuss about the lithium-ion diffusion barrier, which is important for how well LiFePO works in batteries. So in pure LiFePO, the migration barrier is 0.540 eV, which is quite high. This happens because the path for lithium ions are narrow and there is strong repulsion between lithium plus ions and oxygen atoms in the crystal structure. So when vanadium is added, the barrier drops to 0.445 eV. So vanadium changes the structure a bit, making it easier for lithium ion to move by reducing the repulsion and making the lattice more flexible. With nitrogen doping, the barrier lowers slightly to 0.472 eV. The nitrogen causes some distortion that helps lithium ions move better but not as much as vanadium. So the biggest improvement is when both vanadium and nitrogen are added together, co-doping. The barrier decreases a lot to 0.313 eV. So this happens because the structure relaxes and the diffusion path becomes wider. So it making it easier for lithium ions to move. So because of this lower activation energy, the co-dope LiFePO shows the high ionic conductivity, meaning the lithium ion can move faster. So it's important for quick battery charging and discharging. So as a conclusion, geometry optimization shows that all dope structure remain structurally stable with a slight lattice expansion. So the co-dope structure LiBPN exhibit the lowest lithium ion migration energy barrier of 0.313 eV, indicating the enhanced ionic conductivity. So electronic structure analysis revealed the mid-cap state the near Fermi level, contributing to improved electronic conductivity. So overall, the vanadium and nitrogen co-doping significantly enhance the performance of LiFePO, making LiBPN a promising candidate for hybrid and stable lithium-ion battery cathodes. Next, for the recommendation, future research should include the experimental validation to confirm the DFT results, especially regarding ionic conductivity, band gap, and structural stability. For the second one is investigate how doping affects the mechanical properties such as strength and durability of the cathode material through detailed testing or simulation.